thank you for tuning in to Data Innovation Summit 2020. My name is Ahmad Azadvar, and I'm a user researcher at Ubisoft Massive. Today, I'm going to talk to you about predicting self-reported measures of game satisfaction and motivation with only gameplay data as input. First, let's introduce the context of this study. In 2016, we at Ubisoft launched an online multiplayer shooter set in near-future post-pandemic New York City. This open-world game could be played in solo, cooperatively with friends against the AI, or in player versus player modes, and focused on player performance and long-term progression in form of live events, raids, and expansions. This was the fastest-selling intellectual property of its time, attracted millions of players, with some spending hundreds of hours over the years, and provided us with a large pool of gameplay data that we generously refer to as behavioral data in this study. Now, our goal was to see if we can predict players' motivation and need satisfaction in this game without having to survey millions of players, just by going through the behavioral data that they have left behind playing the games. Our overall approach looks something like this. First, gameplay metrics and responses from two sets of surveys or clusters based on the factors that they represent. Then, a pairwise comparison is done to make them ready to be fed into the preference learning algorithm, with gameplay metrics as input and survey responses as outputs. In the next slide, we're going to discuss each of these elements more in depth. The sample consists of 2 years and 30 features worth of gameplay data for 400 plus players. These are clustered onto 4 distinct player styles: Adventurer, which focuses on solo and mission; Elite, which is focuses on performance and progression; PvE All-Rounder, with focus on cooperative game mode; and Social Dark Zone players with focus on versus player mode. Those would be our input variables, but they first need to go through an ordinal processing, which we'll talk about in a few. On the other side, we chose 2 types of survey data. One for evaluation of need satisfaction based on self-determination theory, and the other, a data-driven model based on rating a validated list of game activities, which we derive factors from using principal component analysis on this particular dataset. Self-determination theory is a popular positive social psychology concept that ties one's psychological well-being to satisfaction of 3 basic needs of autonomy, competence, and relatedness. Autonomy is the sense of choice and control. Competence refers to mastery and effective growth, and relatedness is a sense of belongingness with others. This theory argues that in order for someone to be psychologically well, they have to have fulfilled all these 3 needs. The appropriated self-determination theory is an established framework to video games, which are a social environment by themselves, and made an evaluation tool that adds a measure of presence in the virtual environment, which form a 21-item questionnaire we call UPEC. We propose sub-factors for autonomy, competence, and relatedness in the context of a video game. For example, we asked if playing a particular game makes a player feel competent, or if they feel that they're physically present in the game. The second survey is a 36-item list of game features and activities that was statistically validated to make a motivational model of gameplay. Here you can see a correlational table between those factors and 4 factors of UPEC. Some factors derived from that list in the current dataset highly correlate with UPEC factors. For example, fantasy in motivation and relatedness, which is the sense of belongingness in UPEC, understandably highly correlate with one another. Items on the motivation list may look like this. Rate the importance of making an effort to get every collectible in the game, which would load on the factor collect. We can already claim this study encompasses all aspects of player modeling as defined here. We used clustering to define factors of gameplay and survey responses, which are the target of our prediction model. We used behavioral data, or what the player does, to predict what would that player feel about the game. And with these two types of surveys, we are representing both the data-driven or top-down models, as well as bottom-up or data-driven models, which gives us a balanced hybrid. Though our responses are in Likert scale format, which is proven to introduce biases in our dataset, we propose pairwise comparison to address this issue. Especially when rating emotions, Likert scale values could mean different things to different subjects. For example, a rating of 4 out of 5 could mean different things for subject A versus subject B. The distance between the two values also usually perceived differently by each subject. We cannot trust the absolute value, but their relationships. That's why we use a pairwise comparison to focus on preference relationship of the two data points. This makes the dataset a lot larger because for each variable we have to create a comparison matrix, which could be beneficial for a small dataset, this increase of size, but prove problematic for pre-processing of larger datasets. This method also guarantees a 50% accuracy because the machine only has to predict whether A is larger than B or not within the difference threshold that we've defined for it. For analysis, we use support vector machines, a linear and a radial basis function kernel, which emphasizes on the local proximity of data points for our predictions of all factors of UPEC, ease motivation, and groups of gameplay behavior. We used a 10-fold cross-validation that yielded an average linear accuracy of 75% and nonlinear accuracy of 80%. Specifically for UPEC, autonomy and competence showed the highest accuracy rate for prediction. For competence, that was between 89 to 94%, and for autonomy, that was between 84 and 94%. Same method of analysis for motivations showed that fantasy and growth could be predicted with the highest accuracies of between 82 and 90% for motivation. This may show that playing together and the progression in the game are the main factors for players to choose to play this game. Interdimension testing of all 8 factors of motivation and 4 factors of UPEC in testing and training samples are also presented here, and as you can see, factors like social motivation and relatedness in UPEC are still in high interrelation with one another. The main takeaways of this study for us was that the nature of the data we collect from our players, in this case Likert scale, to a large extent inform us on how to treat that data. In this case, we use pairwise comparison and preference learning. We also showed that both theory-driven and bottom-up data-driven models achieve high accuracy in predictions of players' opinion from their gameplay. And that implies that we can organize live events to inform game design by user data in many new ways. This method could also be a good way to examine the theoretical robustness of models and validate data-driven factor analysis done in other studies. We can also argue that the granularity of data collected by both surveys and behavioral data mutually can result in discovery of more specific answers about what players like about the game, what they prefer in it, and their perception of different parts of it. We believed and showed that video games are a good simulated experiences to test all kinds of theories against behavior that are actually happening inside the game. For future work, we also like to observe the player evolution and how they change their behavior, their preferences, and how they perceive the game in different phases of gameplay. And we would also like to look at automated and multimodal data collection from streaming platforms like Twitch and YouTube and social media, and like how people react to different game events and what's happening in the game world in general. For larger scale data sets, and specifically about these kind of problems, we're also looking into deep preference learning to expand our responses to millions of players that we have currently playing our games.
Name a fun game. Chances are someone won't agree with you. Everyone wants to make a game that is fun, but fun isn't the same for everyone. Harnessing innovative machine learning techniques, Massive Entertainment is working with the Institute of Digital Games at the University of Malta to find out what motivates players. Creating content that players will love doesn't need to be guesswork anymore. To predict player motivation, the researchers used data gathered from almost 300 players of Tom Clancy's The Division and ran it through a preference learning algorithm. Using game metrics, play styles, and the Ubisoft Perceived Experience questionnaire, the algorithm was taught to predict presence and the motivations of players as defined by the psychological theory of self-determination, namely competence, autonomy, and relatedness. How you play reveals what you like about Tom Clancy's The Division. Some players like to be social and enjoy the interactive experience. Others might prefer a more chaotic approach. Humans don't think in absolutes. So instead of giving data points absolute values, the points are examined in relation to each other. The algorithm was trained by comparing each data point with every other data point. After training the algorithm, it can predict how a player feels in relation to presence, competence, autonomy, and relatedness with up to 94% accuracy, based only on the gameplay metrics. It's no surprise that your motivations and desires impact how you play a game, but tying specific in-game actions to specific motivational factors has proved tricky. Preference learning and measuring the relations between the data points is a crucial innovation leading to a better understanding of player behavior and the accompanying motivations. The gameplay of players demonstrating a high degree of competence differs greatly from those who lack competence, but there is a whole array in between where the distinctions are not so obvious and plain to the human eye. The ordinal machine learning approach, however, is able to predict complex psychological constructs in all of its subtleties and nuances. And the success of this experiment shows that it is possible to use high-level gameplay metrics and survey-based annotation to model complex emotional and cognitive states. Your gameplay really does say it all.
Thank you for your time. I hope this was useful and we can improve our models, our theories, and our games. Have a good one.